Hello, this is Bruce Moore, founder of StoryWeave LLC and the Theater of Toy Physics. Excuse my voice, I'm having trouble keeping it working these days, so I'll just take it easy. I'm making this video today to illustrate some things about material, and I'll be using this block of clay. As you can see, I'll just review what I've got on the table here. I've got a number of blocks of clay, some the same color. You see I've got a yellow block here. We'll have close-ups of that. Yellow blocks, green, red, blue. There's no significance to the colors except to just keep things separate when we need to, and we're not going to go through all those just today. In this first session here, we're just going to deal with yellow blocks. So I want to take a yellow block here and take it out of the package. Here's my scissors. Okay, I'm going to take it out of the package, get a little closer to you here, and take it out of the plastic. The thing about this block, the important thing about this block is that, you know, it's just material, and one of the confusions is it's clay. One of the confusions that arises with people is the interference that mathematics has with thinking about the reality, in this case, of material, of clay. So the simplest kind of number thing is a measurement. And I'll just tell you that these blocks of clay are each 4 inches long, and you might be able to see that if I get it up real close. It's 4 inches long, and I've got also here I have a little scale where we can measure the weight. And if I put this, I don't know if you can see this or not here, I'll come hold this up too. If I see, I've got a scale here. Of course, it's reading all over the place now because I picked it up. But you see, it gives me a measure. Let me get my hand out of the way. Measure of the weight of this thing. So, you know, those two measures, how much does it weigh? And this, I can tell you, all of these blocks weigh just around 4 ounces. This one, I'll tell you exactly. This one weighs 3.78 ounces. So 3.78 ounces in 4 inches gives you something like a density by length. It's roughly 1 ounce per inch by length. And one of the things that we want to think about here is think about this as a source of energy. And think about it as a source of energy that comes to us every second. We get one of these every second. So, and think of it as coming in increasing length. So every second we get a new one, and it's expanding. The length is getting bigger. There's no need now to think about why do we do that, but just we're going to think that way, that every second we get another length. In this case, the literal length is 4 inches, but we're going to give that label, give that measurement a label. And the label we're going to select for it is c, the label that is usually used for the speed of light in physics. So it's just a label though, and we can say that this distance is c. Well, it's not really the speed of light, obviously it's not that. But we're going to use that label for this length. We're not worried that it's 4 inches, although, you know, we've seen that. And so we're going to utilize that for a demonstration of how we can take this block of clay and we can put it in the form of Einstein's famous energy equation, E equals mc squared. Now, of course, this isn't that energy, and you might originally you might think, well, that's not going to be the real energy equation, and you're right, but it's going to have the same form. And in toy physics and the universes of toy physics, it becomes the equivalent of the Einstein's energy. It's just an inner equivalent. So what we're going to do is take this block, which at this point we've done really no math. We've measured the length, we've measured the weight, and maybe we divided the weight by the length to get that it's 1 ounce per inch. But there's not just a whole lot of complicated mathematics here, a little bit of arithmetic. So now I'm going to switch over. What I'm going to do is move this thing aside, this little weight mechanism, and I'm going to take this clay and I'm going to manipulate it. And I'll tell you, here's one of my favorite things. Look at this guy, a cleaver, where you use that cleaver to do some cutting on this clay. But first, we're going to flatten this clay out into a square. And I have here a little device I made to help me roll it out into squares. You may be able to see that. I don't know. I'm looking, if you see me looking down here, I'm looking at the monitor. I shouldn't be looking at you at all the time. But so we have the ability to roll this clay here. And later we'll use this one, but today we're just going to use it here. So I'm going to switch over now to this scene here. And what I'm going to do is I'm going to put this clay in the middle here. And I'm going to roll it out. So when we start back up, I'm going to have this camera working so we can look down at it. So this is where we're going to cut. Now we're looking at the clay from the top using the phone that's mounted overhead, and you can see it's in that little box. I've got a rolling pin here that you can see too, this little rolling pin. And I'm going to just start rolling it out. And it's a real slow process. Sometimes easier to do with my hands than this, and I think maybe I will. But you see, what I'm going to do is just continually work this thing out until it all fits in that square. And I've got to work that pretty carefully to keep it from going out. Okay, we're going to speed this up a little bit now. So now you can see here that we got it pretty much smoothed out. It's not completely smooth, but we're not seeking perfection here. We're really seeking to convey the main ideas. But the point is that I've taken this yellow block, and it was 4 inches long, and now I've spread that clay out so that it's 4 inches in each direction. It's a square. It's now a square of clay rather than a linear, like a length, a 4-inch length. It's 4 inches on each side. Okay, so now I'm going to start up the other camera and we'll continue from here. I'm going to take this thing out of this little gadget. So here we are. We've got the first a block that just came as a linear length C. And remember, it had a density per inch density, 4 ounces divided by 4 inch, roughly 1 ounce per inch. But now we've taken that very same material, and you can see it's not quite exactly the same, but you see the point. So we've just taken the same material and formed it into a square. And now you wonder, well, is this square like C times C? Not yet. It's a square, C on a side. So C on each side. So one of the difficulties is when a math student looks at the equation C squared, C with a 2 above it, you think C times C, which is correct as far as mathematical formulas, and we'll see what it means in a minute. You probably already know, but the underlying reality in toy physics is that it is a primal material. In toy physics, this becomes representative of an inner energy that flows because of expansion. But right now, the point is that we've got a square. That's it. It is a square. It has nothing to do with mathematics. It has to do with measurement. Now we're going to go now into how it relates to mathematics C times C. So I'm going to switch over again to the overhead view. So this, I know this is really kind of awkward the way I'm doing this, but I'm just getting into these videos and trying to get the content in there, and maybe later we'll get a little slicker with it. Okay, now we're going to process this. We're going to introduce arithmetic. Now, first we're going to do measurements. So we're just going to mark with this little knife. I'm just going to kind of nick right at the 1 inch marks. So here and here and here. And then, so the same thing going this way. Put a mark here and here and here. So now we're going to encounter that some might call dreaded. We enter dreaded mathematics where now we're not talking about length, we're talking about C times C, C squared. And what that really means is that we're just going to quantify this by dividing it into squares. So I'm just going to kind of eyeball it and make a mark all the way across. Not cutting it all the way through, I'm just making a mark across. So those are starting to become square inches or square units of measure. You know, it wouldn't have to be inches. It could be, you know, miles and light years. Okay, this is getting a little out of order, but you'll get the idea. Working with clay is not perfect. Okay, so you know that C squared is 16, and we have 4 rows of 4. So when we start measuring areas like this, the C squared is an area measure, but still we have, this is a block of clay, you see? So now we are going to use the cleaver. And let me just switch to the other camera for a second. We have our square, still a square of substance. It's clay, but we're really wanting to talk about, in toy physics, we're wanting to talk about primal energy that is associated with expansion. And so we want to measure the amount of energy in squares like this. So the thing to remember, though, is that these two sides are both the same, always in a square, C times C. So we have 16 square inches. And we're going to do, here's the step we're going to do. So, you know, right now, what we've shown so far is that, look, you know, mathematics is in a way very, very thin in the sense that it doesn't directly involve material. It measures, it gives measures of material. So it's sometimes difficult to keep in mind what it is that we're actually measuring with mathematics, and you know what the substance is. In this case, it's clay, and we've got a square of it. And sometimes we deal in squares. Think of the squares that you buy to make a patio or to a set of steps. So in this way, we're dealing with energy squares, and that C squared in mathematics is a measure of area. But this is more than area. This is more than area. because it's got depth. This is substance distributed over the area. And it has a density per each square weighs a certain amount. And that's kind of easy to figure out. If it was 4 inches long and now we've made it 4 inches wide, it's the weight of the substance divided by 16. So it's the weight of this clay, which is 4 ounces, divided by 16. So that might have been a little more detailed than you wanted, but here's a trick we're going to do now. And we're going to cut this. And when we cut this, we're going to get a different shape, but keep in mind that it's still this square of material. We're just cutting it into a different shape. But what I mean by a square, it's still this material. We're going to cut it into a shape other than a square. So I'm going to get back under this thing again, and we're going to start it. I'm going to turn this one off. So now is where we really get to use the cleaver, because what we're going to do, this object is kind of strange because there's two measures, but they're always the same with a square. So, you know, a better geometric figure, a better figure to work with instead of that square is what we call in toy physics, and these aren't lining up exactly right because it's not perfect, is a wedge. So we're going to take the two sides of the square and just make them where there's only one measure. So this is now, the measure now is right here. That's the only measure of this. This is called a wedge, and this is a right angle here. You can see here I've got a little thing that has right angles. So that's a right angle, and it's this side, of course, is the same as that. So this is that same square of substance organized into a wedge, and this is called, we call this a Pythagorean wedge, and there's a good reason for that. And that's because if you notice, there's one thing that's really super interesting, that if we say go up and cut 2 inches up, 2 inches up, it looks a little short here just because of the imperfections, but this is 2 inches up. If we cut there, then what we get is another square. This is a 2-inch square, or roughly. Yeah, close, 2-inch square. Hello, this is Bruce again. I made the first half of this video yesterday, and then looking at it, I decided to sharpen up the second half of it. I've moved, as you can tell. I've changed the camera. Here it was further away. But I moved the clay down to where it was before. I want to slow down, well, not slow down. The video yesterday was too slow. That's the problem. I want to go through pretty quickly, but I want to go through some important facts that are crucial to the toy physics work. And so I'm going to switch to this camera now. So what you see in front of you here is what we did yesterday, and I put this little stick here just as a marker. That's where we cut this clay yesterday. And just as a matter of recall, this is a square organized as a wedge, and also we cut a piece off, and this is also another square. So I'm going to give it some numbers here, and the numbers that I'm going to give it, I'm going to say this to this camera. Look, the numbers that I'm going to give it are going to be so recognizable and so outrageous that those of you who know physics will look at that and go, what? And you're right to do that, but I can tell you, this is really meaningful stuff. This gets to some of the essential, very essential fundamentals of toy physics that come way back from the time of Pythagoras. The motto of StoryWeave, or the stance of StoryWeave, is that our children deserve better story about us and this place we're immersed in. And we need to join with the ancients, those of us who can, join with the ancients to think about what they thought about it and to take what they knew and what they perceived during those times and reweave those threads into new story today. So what I'm showing you here is really fundamental to that idea. So if we look back under the camera now. So what you see in front of you here is what we did yesterday. And I put this little stick here just as a marker. That's where we cut this clay yesterday. And just as a matter of recall, this is a square organized as a wedge. And also we cut a piece off, and this is also another square. So I'm going to give it some numbers here. I'm going to say this to this camera. Look, the numbers that I'm going to give it are going to be so recognizable and so outrageous that those of you who know physics will look at that and go, what? And you're right to do that, but I can tell you, this is really meaningful stuff. This gets to some of the essential, very essential fundamentals of toy physics that come way back from the time of Pythagoras. The motto of StoryWeave, or the stance of StoryWeave, is that our children deserve better story about us and this place we're immersed in. And we need to join with the ancients, those of us who can, join with the ancients to think about what they thought about it and to take what they knew and what they perceived during those times and reweave those threads into new story today. So what I'm showing you here is really fundamental to that idea. So if we look back under the camera now here, you can see I've got two measures. There's a red stick. Let me use my little pointer that I have in my hand here. This is the red stick. It represents the distance or length. It's called a level with a wedge from here to there, that distance which we have called C. So I'm just going to put out here like we did. That distance there is, we give it the label C. And I've taken a point here. This is where we cut it yesterday. We cut this clay right there. So it separates another square down here from the larger square. This larger square is known as the total resource. That's the total resource. So the total resource area is C squared. Now we're going to call this is what's going to be outrageous to you. And you'll see why. We're going to call this V. And the area here is V squared. And you remember we could pull this out and rearrange these two blocks, these triangular blocks, into a square. So the black, if you can see under here, we've got a black stick that represents that V, and a red stick represents C. Now the point that I want to make here today is I can overlay this. You see, this is very, very thin. Let me make sure my writings are coming out yet. This is very, very thin. And even though it does have some density, you can imagine that this is really just like pure area. It's thin. It's got very, very low per square inch density. I shouldn't be moving around so much. But it's the same shape as that. So it is this thing that has area C squared and area V squared. This little, you see that I pasted or taped onto there a black measure. So this is the place where it cuts off. V cuts off, and C is the larger measure. So this area is not the same as this clay. This clay now has density. So the total, if you look at the total substance here, that total substance is equal to, and what did we say? It's like 3 point, it's nearly 4. Let's say 4 ounces. It was 4 ounces total for this block. Remember, we had this block here. So it's 4 divided by 16. That's a density times c squared, because each little square here weighs 4/16 of an ounce, or a quarter of an ounce, roughly. And so here we have 4 over 16 times v squared. That is this substance here. So this lower substance, 4/16 times v squared, the overall total resource, 4/16 times c squared. Okay, so what does all that mean? Well, if we hark back now to physics, you see energy equations that are like E equals m times c squared. So this mass in toy physics turns out to be a density. And if you've studied physics at all, you'll know that this mass is a very confusing thing. It's not well understood in physics. You read the descriptions and there's a lot of hand waving about it. It's known for its formula correctness, but it's not understood. Here it's understood to be a density, and that really makes a difference in the overall understanding. Okay, so now we've got areas, and this is the usual Pythagorean theorem I'm going to show you. I'm going to show you now what Pythagoras says about things here. So the question is, there's one question here. If we take away this now, and that's mv squared, you recognize that as kinetic energy, some of you? That seems crazy, but that's what we will see it turns out to be in toy physics. This portion here supports constant velocity. Then Pythagorean theorem would say that, okay, this was the portion that we took off, and that's a black portion down here. Let me make sure I'm in I got to move it up. Sorry, I'm looking at my thing here. Let me get it up where we can see. I need to move this out of the way. So taking those measures now, see we have the black portion here. The red is the total, that's what we had, that's this, C. And so we've taken a portion away, and we have something left. So this something left, we know then from Pythagorean theorem that this material here that's left, can I see that material? Yes. I'm looking up at my camera to make sure I'm in the field of vision. We can fashion this material, this clay, into a square that's of this measure here, which amounts to the Pythagorean theorem. Now you see in mathematics, what you would see is that you calculate this as the square root of this square, c squared minus v squared. That would give you the amount left. And if you look at relativity theory, what you'll find in there with Minkowski, a separation measure that says s squared is equal to c squared minus v squared. But they are strictly talking about here, Pythagorean theorem is about distances, these measures. And in our energy conversation, this is about the blocks themselves. So, we have this block down here, which we can make into a square. that's the part that we're using for velocity. And the original was this total part here. So now the question is, can we form this material into a block, square? And you know, it does. Both of these have the same density. That's why the two terms are both 4/16. So, and the answer from Pythagoras is well, you know, it's got two answers. Yeah, we can form this block into a square, and it's going to have that length. But if you want to pursue the mystery of the ancients and try to understand it better, the answer is really also a no, because this number is not necessarily a rational number. So we can get close to it, but we can't ever. Sometimes, very often, the remaining material can't quite be formed into a perfect square. We can get it as close as we want. Now, what I'm going to do offline, I'm going to stop this now. I'm going to take this material here, which is the part that's remaining after we took off the velocity portion, and I'm going to form it into a square that has this measure. And we'll see that, and that's, you know, that takes a little bit of doing. Here you can see it took, you know, they all have the same density, but I had to take little pieces and put them in there. But you can see that this is the original block of clay, same amount that's in these. This is the part that we took off for velocity. So this is, in toy physics, this will be, it may support something other than velocity. There is something else called compression, which appears in toy physics from the geometry, but it doesn't appear in actual physics like that. But so we just think about velocity here. This supports uniform velocity. This is internal energy, remember. Shouldn't use that red thing. I should use my pointer. This supports internal energy, supports velocity. This is the remainder. So this is relational energy. And in toy physics, this is like the carrier of that we would think of as fields. It serves in carrying light. It carries gravity. This is a carrier, or this energy supports a carrier. It acts in the sensory outer dimensions. This is an inner dimension phenomenon that basically propels an atom. That sounds outrageous, and that's one of the reasons that you should look into this. So the point I want to stress is that this looks outrageous. You know, we're saying mc squared is equal to, or rather ms squared. That s is like a measure we find in physics for separation. M times s squared, that we're saying m is really a density, and ms squared is equal to mc squared minus mv squared. And so we've got mass in there now. And physics doesn't have that. It shows a relation s squared equals c squared minus v squared. But it doesn't connect it with the energy mc squared or mv squared or ms squared. It doesn't do that. And the reason is the formulations of energy are they're partners. But the external energy comes from empirical studies of force and motion. And this internal energy comes from this toy geometry, which is an alternative to vector space geometry. It is based on fundamental root concepts that are simply not in physics. So we derive from first principles geometry that exhibits this behavior, and it exhibits, through the Pythagorean Theorem, it exhibits this characteristic that when kinetic energy, when you move something, when something is moving, then a portion of the inner energy is used for that motion. So kinetic energy is internal energy that's taken away from the full resource of energy from expansion, and it leaves less for relational web. The relational web, this is an expanding web. That's what a toy physics universe is. It leaves less for that, and that means that surface distances decrease, time, the time measure, which is just a redundant measure of distance in terms of light, that decreases also. I know all this sounds like gibberish, but just focus on what I've shown you here. With clay, you have a substance. We've taken it and put it into a wedge. And then from there, we can manipulate it, and we get equations that look like physics. Now, I haven't shown that, haven't justified that, but we're going to do that. Now, I wanted to show you one other thing. I'll call that clay thing a wedge, but here's some more wedges. This is a container, and later I'll show you some demonstrations where we fill these containers with cat litter, and you have the same thing, same kind of deal here. I'll show you. Let me pick up a bigger wedge. This is the bigger one, container, and we can fill this with cat litter up to a certain level, and we can pour a portion of that litter, get cat litter, into here, and when we do, we've got a level in this container that tells how much material there is in. The density is determined by the cat litter and the width of this container. And so, we have the same kind of thing, but it's in a more fluid form. The clay is not really as fluid. So the fluid form is nice for demonstrating flows and things. And here we see the same kind of thing as the wedge. That's a wedge, but if we turn it around and make it a square like this, it's a square just like we had with the clay. So the wedge is really, and the Pythagorean allocation, this is called Pythagorean Resource Allocation, because whether it's clay or cat litter or energy, we have a total resource that we're allocating parts for. This is going to be the sustainer of constant velocity. This is relational energy that will determine distances on the surface. That all sounds wild, but that's what happens, and it's rigorous mathematics that isn't nearly as complicated as the mathematics of physics, because it doesn't jump up to four-dimensional pointing mathematics, which is impossible to imagine. Rather, this mathematics uses one inner dimension. You remember that's like the one that was here, vertical, and three outer dimensions, which are our sensory dimensions around us. Okay, so that's a lot of information. I hope it was a little bit coherent. I know it says some things that you just can't believe, but hopefully that will entice you to look into the details, to study this stuff with me, because this is in the toy physics book, but the toy physics book is very difficult to read. I wrote that book to basically chronicle the results, and in doing so, I wrote them in a way that is like a resource to me. I did the best I could in writing it. I thought it was really clear, but I lived with this stuff for 14 years, so I know now for sure that it's, without some help, it isn't something that people are just going to casually read. So I hope you've gotten something from this. Thank you for listening. And I do have a website, StoryWeave.com. It's getting in order. It's not really there yet, but it will eventually be the carrier of this, at least pointers to this series of material, or it's the place where you can get a series of explanations of toy physics, and you can get pointers to the videos on YouTube, and you can download PDFs, and you can sign up to study with me if you like. So thanks so much. Have a good one.